Welcome back everyone to 6.4. In this video we're just going to go over 4 more examples to wrap up this section. So let's get to it by reminding ourselves something about this idea of logarithmic differentiation. Alright, so we had 3 steps to logarithmic differentiation. The first was apply logarithms, right? So we do this to both sides of the equation, and then we use laws of logarithms to simplify this down. The second step is to differentiate. We're going to differentiate implicitly with respect to x, and then finally solve for y prime, right? Solve for that derivative. So we applied it down here in 6.2.10, right, to this example, but we're going to see here in 6.4 we have a little bit more complicated of a situation where we have to apply logarithmic differentiation. In this one, I mean, it would have been a pain not to, but we technically didn't need to. All right, so let's get to it. This one tells us use logarithmic differentiation to find the derivative, this dy dx. And notice that we have a variable in both the base and the exponent. And the claim is whenever that happens, we kind of have to use logarithmic differentiation. So even if it didn't say use logarithmic differentiation, you could identify, hey, I need to because there's this variable in both the base and the exponent. So let's apply a natural log to both sides. And the advantage of doing it in this case is that, well, you can bring that exponent down. Right? One of the properties of the logarithm says that, hey, you can go ahead and take the exponent and make it the constant. That was called the power rule. Okay, now at this point, we would need to differentiate implicitly with respect to x. So if I take the derivative of the left-hand side, I'm going to get 1 over y times y prime. So that y prime is another way to write dy dx, remember that. And then on the right-hand side, well, I'm going to need to use a product rule. So let's see, the derivative of 1 over x is negative x to the negative 2 power times the first, right? So the derivative of the first times the second plus the first times the derivative of the second. That's the product rule. And there we are. And now we're essentially done, right? The last step is to solve for y prime, or dy dx. So I'm going to multiply by y. Now remember what y was, right? Y was this 1 plus x raised to the 1 over x. So let's rewrite it, so that way we have just x's in our equation. And then, well, it's just this. So I'm going to use the magic of technology to copy and paste, right? So there is y prime. And we could spend some time simplifying and stuff, but really, this is what y prime is. Okay. Now moving on, let's try a few more examples. These ones won't necessarily have so much to do with logarithmic differentiation, but I mean, we learned about exponentials of other bases and logs of other bases here, so we should get a little bit of practice. So here I have a nice function, 4 to the x and x to the 4. So I'm going to take the derivative of the easy one first, right? The easier one is this power rule, right? The x to the 4, its derivative should be 4x cubed. Now this other one is exponential, so I have a rule that is supposed to be a to the x times the natural log of a. Well, in this case, a is 4. So there we are. All right, let's try another one here. In this case, again, my a here is 3. So it's going to be 3 to the x, right? Or 3 to the sine of 2x, it's a more complicated one, times the natural log of a. Again, my a is 3. And then now I have the chain rule. So the chain rule says I need to take the derivative of the inside, which should be the cosine of 2x, and yet I have another chain rule that says I need to multiply by 2, the derivative of its inside. Whew. So when it's all said and done, let's kind of gather all the constants. So 2 and natural log of 3. And then times cosine of 2x, and then times 3 to the sine of 2x. So I'm just rearranging things a little bit, make it look pretty. All right, let's do one more here. We have a variable in the base and in the exponent. So that's telling me, right, even though it doesn't say use logarithmic differentiation, I'm thinking, I should use logarithmic differentiation. So let's try it out here. The first step is to apply a log to both sides. I'm just going to call this g instead of g of x. All right, and now, well, I could do a derivative of the left-hand side if I wanted. So it's going to be 1 over g times g prime is equal to, and, well, actually, sorry, I skipped a step. Let's just keep this the natural log of g, and then let's use the properties of logarithms like we're supposed to simplify this. And the whole point of applying this logarithm is so that I can get my variable out of the exponent. Now I can take the derivative. So when I do that, again, I have a product rule. So the derivative of the first times the second plus the first times the derivative of the second. And watch out, there's a chain rule, right? So I have to do that times 2. And notice there's a little bit of cancellation that happens here. So I can get g prime is equal to, and g, right? So I would multiply by g on both sides. And then this is 3 times the natural log of 2x. And now the cancellation that I had talked about before, right? These 2 cancels, these x's cancel, so the only thing that's left here is really the 3. So plus 3. And there we go. That's how we can differentiate this function. All right, let's try one where we actually have to do an integral. Integral here. So hopefully we stare at this for a little while, and hopefully we agree that maybe some U-substitution is a good idea here. I see this x squared, and I see its derivative. Well, not exactly its derivative, but close enough, right? So I see this x down here, and I can think that, hey, this will get absorbed. So that's what's leading me towards a U-substitution. So let's try it out here. So u is going to be x squared. Du is going to be 2x dx. And I could write this, right? I have the x and I have the dx. So I could write this as 1/2 du is equal to x dx. So that way I can trade in those pieces for half du. So let's go for it. So this is going to be the integral of 5 to the u, right? That's x squared is u. And then I can trade in my x dx for 1/2 du. Okay, now this is something that I can integrate. So I can integrate this. The integral of 5 to the u is going to be 5 to the u divided by the natural log of 5. Have this 1/2, a constant, just hanging around, and of course my plus c. So now I can rewrite this as 5 to the x squared. Let's combo these things. Let's make it 2 times the natural log of 5 plus c. All right, and there's my final answer. Let's do one more problem here. Another integral. Oh, and in fact, this one also looks to me, right? I see the sign and I see its derivative, cosine of theta d theta. So I'm thinking again, hey, I should try U-substitution. So u will be sine of theta, du will be cosine of theta d theta. And now I can go ahead and substitute in, instead of that cosine of theta d theta, I'm going to just trade that in for du, and this is going to be 2 to the u. Again, I know how to integrate exponentials, so this is going to be 2 to the u divided by the natural log of 2, plus a constant of integration. And then I need to substitute back in. So instead of u, I'm going to write sine of theta. And that's all there is to it. All right, we have officially conquered 6.4. Go ahead and take a break before starting on your homework. I'll see you next time in 6.5, exponential growth and decay. See you then.